Good morning, everybody. Good morning to everybody. Welcome to this 7th day of the hour of the Quantum Espresso School. Today, the morning will be dedicated to the use of quantum espresso to study magnetism. The lecture of the morning will be done by Dr. Alessandro STROPPA from CNR-SPIN, L'Aquila, Italy, and I leave the floor to Alessandro. And please, Alessandro, you can start.
Thanks. Thank you, Pietro, for the introduction, and good morning to everyone. So it's a great pleasure for me to give this lecture. And first of all, I would like to thank Professor Stefano Baroni for letting me join this wonderful team for the organization of the school. So, as I mentioned, I would like to give a very brief, a very broad overview of magnetism, starting from basic theoretical arguments and then going towards more practical aspects, that means computational magnetism. So I'm Alessandro Stroppa from CNR, so let me say something about my institution. National Research Council is the largest public research institution in Italy, and it performs multidisciplinary activities, so you may have a look here. And in particular, we study physics and matter, and chemistry and materials technology. And the institution has several research centers all around Italy here. And in particular, my institute is called SPIN. Well, SPIN here is not really the spin of the electron, but it's an acronym for superconductors, oxide, and other innovative materials and devices. This institute is relatively new. It was established in 2010, so you may have a look here for the activity of our institute. And again, it has several centers, and I'm located here in L'Aquila. L'Aquila is a very nice and historical city in the central part of Italy and in the Apennines, and very close to Roma. And the mission of the institute is to study innovative materials and their application in the fields of electronics and energy. So, as you know from the talk by Professor Blugel last week, magnetism plays a very important role in modern device applications. So this leads me to the outline of this lecture. So in the first part, I will give, as I said, a broad introduction, starting from basic arguments, and I tell you clearly, I want to reach any one of you. So I apologize if some of you actually will get bored by this part. So the core argument of the lecture is actually relativity and direct equation. We want to have to give an introduction, a formal discussion about this equation, and then we will move to density functional theory, and in particular to the generalization of it to meet magnetic material. I mean, the way we describe magnetic materials in density functional theory. And this requires that we distinguish two different frameworks, collinear and non-collinear magnetism. And at the end of the lecture, I will give broad examples here, and then I will basically introduce to the second session, the hands-on, which will be given by Pietro De Lugas. So magnetism, magical yet practical. So probably the first report on magnetism was given by Thales of Miletus, reporting the attraction of iron by magnetite. It is quite impressive that it took about 2,500 years to understand the microscopic origin of these phenomena and about the attraction of stones. And indeed, I want to mention some milestones that were important in this history of science, in particular that the Treatise of Electricity and Magnetism by James Clerk Maxwell. It is a very elegant and beautiful mathematical theory about the combination of electricity and magnetism, and already Einstein noted that this theory was already in agreement with the relativity principle for the constant velocity of light, and also because the theory is already ready to be recast in covariant formalism. And at the time of Maxwell, actually, Boltzmann was already impressed by this theory and commented, "Was it God who wrote these symbols?" So the next milestone is, of course, the quantum jump in physics. I mean, the years 1925 to 1928, where there was the development of quantum mechanics and the idea of spinning electron given by Anlebeck and Gasmith in 1925. But it was only in 1928 that Paul-Adrien Maurice Dirac put on a mathematical framework the wave equation for the electron, which is coherent with the Einstein relativity theory. So spinning electron, we have to go from classical towards quantum mechanical magnetic moments. So we have here our toy model, which is essentially an electron which is moving around the nucleus, and it gives rise to an electrical current I. And then to this physical moment, as a physical system, we can compute the orbital angular momentum, and then we can associate a magnetic moment here. Here I is the current, and S is the area of this loop-oriented area. The keywords that we have to consider in order to understand the magnetic phenomena are symmetry, relativity theory, and a wave equation. And then from we can do some algebra here. We can combine the magnetic moment and we can relate to the orbital angular momentum in this physical system. And then we should be able to get some confidence with this intrinsic property of the electron, which is called spin, where we have two relevant states, spin up and spin down. So materials, nuclei plus electrons. Then from spinning electrons, we have to go towards spinning atoms. And crystalline materials are essentially a regular array of atoms. And then they can bond, and if there are atomic spins, if any, they may order. Then they give rise to magnetic materials. So here, I just show some spin configurations, and for us now they are just a set of arrows, and I don't discuss them now, but at the end of this lecture we should be able to get more confidence with this set of arrows and how we can compute these by computational magnetism. So we have a microscopic properties which give rise to a macroscopic properties in terms of magnetic moment per unit volume. That means the magnetization. So you are familiar with this hysteresis loop. So we have two relevant directions, plus m and minus m along a reference axis, and then an external field H which can tune this magnetization. Well, this bistability actually opens the door to this magnetic world in terms of applications. So you may have here high-speed train, the Shanghai maglev, or you may have several device applications in terms of storage and memory devices. So let me summarize this first part. Intrinsic property of the electron, spin, magnetic moment. We are interested in materials, and then we realize that this microscopic property give rise to some macroscopic property in terms of ferromagnetic moment per unit volume. And then we have this hysteresis loop. So we are interested in materials properties. These long range properties is usually called a ferroid property. In this case is about ferromagnetism. We can have also coexistence of different ferroic properties, and then we call them multiferroics. And then we are interested in basically in application. So we study materials, in particular magnetic materials, for device applications. So for studying materials, we know we need the Schrodinger equation, which governs the description, macroscopic description of these physical systems, or equivalent formulation of it in terms of density functional theory. So microscopic origin of magnetism, as you know, the charge and the spin are the basic building blocks for the modern understanding of electronic structure and magnetic materials. And I want to recap something about two toys model which were actually introduced and studied at the beginning of quantum mechanics in order to understand how this magnetic moment due to the spins of the electrons actually can interact among them. So here we are considering the helium atom and then the hydrogen molecule. Essentially, we are going to discuss two keywords now, exchange interactions, and then the other relevant keyword, spin orbit, will be introduced later. Exchange interaction is basically the large magnetic interaction, and it's the origin of the alignment of the spin system. So without this kind of interaction, there will be no spontaneous magnetization. The spin orbit interaction, as you know, is a very teeny interaction on an energy scale much smaller with respect to the exchange interaction, but still it is important because it gives rise to the magnetocrystalline anisotropy. So it defines some preferential direction in the crystal where the spins prefer to align. So the toy example, we have to write this electronic Hamiltonian for an atom. So we are all familiar with this description here. So we have this kinetic part, the electron nucleus interaction, and then there is this electron interaction, which is actually very important at this level because it is the source of the interaction between spins, even if there is no spin-dependent interaction here. So actually this part in the Hamiltonian is responsible for what we will call exchange interaction, meaning interaction between spins. So we can rewrite this Hamiltonian in a slightly different way by using some central field approximation. So we split in a sum of single particle Hamiltonian, then we put here the remaining part, H1. Then in this central field Hamiltonian, we can write the single particle wave function by separating the variables. So we have here in the orbital sector, we have radial part and then angular part. Then we have these Q functions, which are the so-called spin functions, one electron spin functions. So this is actually called spin orbital. So you know that there are two relevant states, alpha and beta, and these are the eigenvalue of the relevant spin operator as zeta. Here we take h bar as a unit. And then we can collect all the variables in a single one, which we call here A. So there is another important point in quantum mechanics, which is the so-called symmetrization postulate. You know that in quantum mechanics, identical particles are indistinguishable. And then in this case, actually this postulate tells us that the only physical wave functions are those which belong to the so-called symmetric or anti-symmetric representation. So in particular, then there is an important theorem in quantum field theory that means the spin statistic theorem, which connects these statistical properties, that means these anti-symmetric or symmetric properties of the wave function with the spin. So in particular for fermions, we know that the wave function must be anti-symmetric. This means that if we exchange the two variable, the variable of the two electrons, so we are focusing on two electron case, actually the wave function change sign. And then this spin statistic theorem connects these to half integer spins. Now for fermions, we can specify for the case where the orbital part is required to be symmetric and the spin part is required to be antisymmetric in order to have an overall antisymmetric property of the wave function, total wave function. Or we may have also the possibility to have the orbital part antisymmetric and the spin part here symmetric. So if we do so, essentially we can separate the two part, so here symmetric part, and for the spin part we have the so-called singlet, S is equal to 0 and MS is equal to 0, where S is the eigenvalue of the total spin operator of two electrons. In the other case, we focus on antisymmetric part in the orbital part, but for this spin part, we have a symmetric wave function, spin function, and here it's called triplet. So we can play with this symmetrization postulate, which is another description of the exclusion principle, and then in dependent electron approximation, we can split the total wave function in the product of the two single particle wave functions. And then we can play with this linear combination in order to have the required antisymmetric properties of the wave function. So in this case, if we exchange the two variables of the two electrons, then the wave function change sign. So this is a fundamental requirement from quantum mechanics in order to have physical states representing our system. Then we can apply this in the helium atom, and it was done by Heisenberg at the beginning of quantum mechanics in 1926. And then actually Heisenberg introduced this word exchange. And in particular, he was focusing on the ground state, where in this independent particle approximation, we have the two electrons occupying the 1s state. So you can refer here electron configuration like 1s2 or 1s1s. But then he was also studying the emission lines after exciting one electron in an NL state. And these emission spectra were separated in singlets and triplets. And actually, Heisenberg, in his studies, noted that in the ground state, there is the absence of the triplet states. And actually, this is required by a Pauli principle. And then he noted that there is a relative shift between these two energy terms, which actually belongs to the same electron configuration. So this is a one electron excited states, 1s, 2s. And then there is another shift for the other electronic configuration, 1s and 2p. So what do we really mean with exchange here? And this was pointed out by Heisenberg in more details. So this is just qualitative argument. We don't go into the technical points for this discussion here. So, but anyway, we can write an H0 Hamiltonian, which is simply the sum of one particle Hamiltonian here. And then we have this electron-electron interaction. Now, we can consider the ground states, and then we can build a trial wave function in order to evaluate the mean value of this Hamiltonian starting from the mean value of this H0. So for the ground state, we have actually only one possibility. That means requiring that the orbital part is symmetric in the space part, space variable, and the spin part is antisymmetric with the two electrons in 1, 0, 0 state. So here is n equal to 1, L is equal to 0, and ML is equal to 0. And then the only possibility is this wave function for the ground state. Then you can evaluate this H0, then this correction term, and then you have this A1 energy term. Then we consider now the single excited states, I mean the electronic configuration where we have 1s and NLM state. So we excite one electron and then the other electron is in 1s state. Then if we do so, actually in this case, we can build two trial wave functions. One is called singlet here because the spin part is antisymmetric, and this requires that the space part is symmetric. Or you can also build another trial wave function, which is the triplet, where the spin part is symmetric and the orbital part is antisymmetric. Then we can evaluate first H0 by using these two trial wave functions, and then we can evaluate the correction due to the electron-electron interaction. Well, now things becomes a little bit interesting, because if you do so, then you have this common term here, high, and then plus j and minus j. Then you can even express here high as an integral between this charge density, And this J is not actually an integral between two charge density, but it's something very similar. And actually, we can call this like the first term is the so-called the Coulomb integral is a positive. It represents the electrostatic Coulomb repulsion between the electron density. So this is a square modulus of the wave function for the electron in 1, 0, 0, and for this is for the charge density of the electron in NLM state. But here we have the exchange integral. That means it is the energy associated with the exchange of the quantum states between two electrons. So in this term, we have R2, R1, but in this term, actually, we exchange it to spatial variable, keeping the same reference states for the electrons. So now in the singlet, what happens? The space part is symmetric, so the electrons tend to be close to each other. Actually, they can be close to each other. Then we would expect a large electrostatic repulsion. This actually is not the case for the triplet, where the space part is antisymmetric. So if the electrons go close to each other, actually the wave function goes to 0. Then the electrons tend to avoid each other, and this will lead to a smaller electrostatic repulsion. So I think we can summarize. So we can put things together like a piece of a puzzle here. So we have a reference state, then we have a correction term, which we call is a common term, ES plus I. But then if we focus on a triplet, we have a lowering of the reference energy level here. And then for the singlet, we have an higher repulsion between the electrons. And so we go up in energy. And then we can call this splitting actually the 2J, which is the energy difference between the singlet and the triplet energy term. So I think we can stop for a while, and then we can take on the following messages. It's like a pictorial equation. So Coulomb interaction between electrons plus symmetry. What do we mean symmetry? The Hamiltonian is symmetric under the so-called permutation group. Then symmetrization postulate, there is the requirement that the only physical state of the system are, for the case of the fermions, are anti-symmetric representations of this symmetry group. And then this gives rise to so-called exchange. Essentially, starting with some interaction, which is just a Coulomb interaction, no explicit spin terms, we end up with energy separation between energy level, which depends on the relative orientation of the spins. So this is quite interesting. Indeed, Heisenberg then put forward this model and consider a slightly complicated model, which is the H2 molecule. So here we have the graphical representation of this molecule, and we will briefly discuss the solution in the Heitler-London approach. And in order to simplify the discussion, we go back by removing one electron. So we construct useful orbitals, actual molecular orbitals, by using this linear combination of atomic orbitals for the H2 plus model. Okay, so here we have a bonding linear combination. That means the sum of the two orbitals where the electron is on the left, belonging to the atom on the left or to the atom on the right. And then here we have anti-bonding orbitals. So here we have a pile-up of electronic charge, and then it gives rise to the bonding, the chemical bonding, while in the anti-bonding state, we have a depletion of electronic charge. So by using these orbitals, molecular orbitals, then we can go back to our relevant system, that means H2 molecule here. So the trick is, again, we can focus on the sum of the two single particle Hamiltonian. Then we have all these interaction terms here. Then we can write it again in a slightly different form in order to highlight a term which can be referred to H2 plus, another term which can be referred to H2 plus, that means electron on the left, electron on the right, like two relevant models here. And then we have this electron-electron interaction that for the moment we just leave. We will consider later. And this is the nucleus-nucleus interaction, which is rather a constant if we fix the internuclear distance. And then we use the symmetrization postulate. As before, we focus on the ground state, and of course, the ground state, the lower energy, is expected when we consider both electrons in the bonding orbitals. And this means that the only possibility is to have a symmetric combination of the two. If you try to have an anti-symmetric combination, then it is 0. And then the spin part requires to be anti-symmetric. But then we can excite one electron, and then we can focus here on the triplet combination. That means we require the spins are symmetric. The spin wave function is symmetric, while the orbital part is anti-symmetric. Then we can go back to the definition of these molecular orbitals in terms of linear combination of atomic orbitals, and then we have, if we focus on this single part, which is the ground state, actually we can have a first part which is called Heitel-London, where the two electrons are actually described as between the two nuclei, or we have also ionic terms, where the two electrons are either localized on the left or on the right. Actually, these ionic terms are quite unfavorable, especially in the dissociation limit. So in the Heitel-London approximation, actually one forget these ionic terms, keeps only the first part of the wave function. So this is the so-called Heitel-London approximation. And then one can do the same approach also for the triplet, for the first excited states of this molecule. And then, as before, we can evaluate these mean value of the Hamiltonian, the full Hamiltonian, putting back again the electron-electron interaction. As you see, we have again quite complicated representation here, but you see that there is common terms here, Coulomb term, and also X is the exchange term. So we have energy levels which are different if we consider singlet or triplet. So we discussed the Heitel-London approximation, and we cut now the long story short, and we can basically summarize what we learned so far. So we can focus on a relevant energy split, which is the singlet minus the triplet, and we call it 2J. And then we focus on helium atom in terms of energy separation of singlet triplet of the excited states. In that case, J was positive, meaning that the triplet is lower with respect to the singlet. But in the H2 molecule, we were focused on the energy separation between the ground state and the first excited states. In this case, J is negative. So we can forget all this formulation now, and we can describe here the take-home messages as before. Essentially, we are focusing on exchange interaction. That means starting with the Hamiltonian, which does not depend on the spins. At the end, after our manipulation of the Hamiltonian calculation and so on, we arrived to spin-dependent interaction, which shows up in terms of energy level, which depend on the relative orientation of the two spins. J can be either positive or negative. And this actually introduced the so-called Heisenberg approach. That means, well, since we have in two relevant cases, helium and H2 molecule, the possibility that the energy terms depends on the relative spin orientations, can we map this model, this Hamiltonian, another effective Hamiltonian, just focusing on the spin variables? And this was done by Heisenberg for the first time, and essentially he writes this effective Hamiltonian where this exchange part is parameterized in the form of an interaction term S1 dot S2. So these are the spin operators. A is a constant, and in particular case is equal to minus 2J. Then in quantum mechanics, one can introduce this total spin operator, the sum of the two. Just skip formalities here, Kronecker product, and so on and so forth, but then we just focus on qualitative arguments. So we can square this operator, then we have this relation. We can study the eigenstate and the eigenvalues, where the eigenvalues of this operator are actually S equal to 1, which correspond to triplet state, and S equal to 0, which correspond to the singlet. But now we can, then we know this from quantum mechanics, and then we can actually focus on this S1.S2, because we can express this S1.S2 by using this other expression here. And then we can focus on eigenstate and eigenvalues of this S1, S2. For the triplet, well, it happens that this operator is already diagonal on this basis, and then we have here the triplet eigenstate with the eigenvalue S equal to 1 for S dot S2, where the eigenvalue here now is 1/4, and for the singlet, we have eigenvalue minus 3/4. So essentially, we can use this energy term, this interaction term, and we can write this energy level diagram for A positive, meaning that the singlet is now at lower energy, and the triplet is at higher energy. So actually, we can focus on these two variables. We can forget all the rest is basically constant, but if you are interested in energy separation between these relevant states, then we can mimic this exchange effect in terms of this exchange Hamiltonian, which is called essentially a Heisenberg Hamiltonian. So this is for 2 electrons. We can generalize for many electrons, so we can write a kind of generalization where now we have a matrix which is actually symmetric, Jij, and then essentially one in principle can write these exchange integrals, but in an operative way, one actually maps this Hamiltonian into total energy calculation by DFT in order to have an estimate of this Jij. And then one can write this energy separation in terms of the eigenvalues of S1.S2, and actually by this, the previous definition, we recover these two times J12. So actually, this Heisenberg model can account for exchange interaction by explicitly coupling the pairs of spin or eventually atomic moments. So J can be positive for ferromagnetic coupling and negative for anti-ferromagnetic coupling. And this coupling can be defined intra-atomic, so spins in the same atom, or eventually coupling between spin in different atoms. Then we have interatomic exchange. Actually, this opened a quite large zoology of exchange interaction. So one can refine the model for different type of interaction in different materials. So double exchange, the direct exchange, super exchange, and so on and so forth. One can introduce even higher terms in the spin-spin interaction, but we don't go into details here because we want now to close this chapter in exchange interaction. We want to open another chapter about spin-orbit interactions. So it deals with the interaction of the spin with the orbital angular momentum. Usually it is from 10 to 100 times smaller than the exchange, and still the spin-orbit coupling is very important for magnetism. So there are several ways that we can use in order to introduce this spin-orbit interaction. There is this semi-classical model. So we go back again to our model of this electron which is moving around the nucleus. Then we have this relation for the absolute value of this magnetic moment in terms of current and area. And then we have this relation that we know from classical electrodynamics. But now this current loop actually give rise to an orbital magnetic field, a magnetic field generated by this current, and we know that a magnetic moment can interact with a magnetic field by this Zeeman interaction. So from quantum mechanics, now we borrow the expression. Actually, we will explain why we have this expression here, but for the time being, we just borrow from quantum mechanics. The magnetic moment associated with the spin is just this factor times S, which is the spin of the electron. Then we can evaluate the orbital, the magnetic field generated by this current loop. Then we can relate it I to the magnetic moment of the spin. Then we can put everything together. Essentially, we are now expressing this B field in terms of the angular momentum. So if you consider previous formula, you can easily end up in this formulation. But now, by using this Zeeman interaction, you can consider this expression here times this orbital magnetic moment, and then you have something like L dot S. Actually, this is called spin-orbit interaction, and it is introduced here in this semi-classical model. And if one studies this interaction in quantum mechanics, actually one realizes that this is very small splitting for lighter atoms like hydrogen and helium, but it can rapidly increase in energy splitting when we consider heavier atoms. And so this is a plot reporting the energy splitting between the relevant states as a function of zeta. Then there is another way that one can use to introduce this spin-orbit interaction by using some relativity concept. So we have the electron which is moving around the nucleus, but we can keep now the electron at rest. That means we consider the reference frame where the electron is at rest. But now in this reference frame where the electron is at rest, it sees an effective magnetic field due to this relativistic transformation of the electromagnetic field. Now here there is a factor of 2, which is due to the Thomas precession here. So, but anyway, if we take this relativistic transformation of the field seen by the electron, then we consider the electron generated by the nucleus, which can be expressed in this form. We put everything together here, and we can express P in terms of V by this linear momentum m times V. And then for the electrostatic potential, we can express in this analytical form. And then again, putting everything together, we can express the interaction of the spin of the electron where at the reference frame where it is at rest with the field that it sees due to this relativistic transformation. If we put everything together here, then we end up again with this S dot L. So now here we understand that this spin-orbit interaction has something to do with relativity, because this is a strong argument that actually justify the existence of the spin orbit. As I said, it's rather small, but for 2D transitional metals, and then it can be quite large. It can start to be non-negligible when we consider atoms with increasing zeta. So one can write the Spinobit Hamiltonian in the following terms. So one can group the prefactor here with this constant, and one can evaluate as a bracket between the relevant spin orbitals here. And this L dot S can be expressed in these quantum mechanical operators by using by introducing J, which is the sum of the angular momentum, the angular momentum operator, and the spin or orbital momentum here. And then from quantum mechanics, we know that there are possible J, minimum, and max, which are related to the L minus S, and L plus S. And then one can express these L dot S by using these quantum numbers. So, importance of spin orbit, well, essentially, suppose that in the crystal we have some preferential direction for the orbital angular momentum. Then this L dot S actually defines some preferential direction for the spin, because you know from these interaction terms that S would like to stay along the direction of L in order to minimize the energy. Otherwise, we can have this is called easy axis. On the other case, we can have S, which is perpendicular to L, and then we can have an increase of the energy due to this interaction term. And then, in this case, we have another axis. Still, this term is small in terms of energy separation, but it gives rise to an important phenomenon in solid, which is called magnetocrystalline anisotropy. We will not discuss in details this time because actually it's quite complicated by formal point of view. But now we have another important ingredient, which are the ANS rule. I just remind you what we mean with the ANS rule. If we have some electronic configuration, then we know that for a given electronic configuration, we have to maximize the S, that means we have to maximize the spin multiplicity, and then for fixed S we have to maximize the angular momentum multiplicity, and then when we act with these two variables, we have that the lowest term will have the lowest J in case the shell is more than, sorry, the largest J if the shell is more than half full, or the smallest J in case the shell is less than half full. Then another pictorial equation, exchange plus spin-orbit interaction, actually give rise ANS rule. And why these ANS rules are important, especially when we are considering solid. Of course, in atomic physics, they are very important. They give rise to several phenomena. But when we have an atom in a solid in crystalline environment, sometimes these d electronic states are split by the so-called crystal field effect. It means they are not degenerate anymore, but we have this T2G splitting and AG energy splitting separation. And then we have to keep in mind this answer first rule. That means we have to maximize the spin multiplicity. So we can have several cases. That means case which correspond to high spin, other case which correspond to the low spin. For instance, for the low spin, we have the possibility here that the crystal field splitting is very large with respect to exchange interaction. So we have to keep in mind the first ANS rule, and then we have to keep in mind the Pauli exclusion principle. So if we are considering enough about approach here, so we are filling these electrons in these energy terms here. So we start with the lowest one, which is a T2G terms. Then, since we have the crystal field splitting is very large, then the atom prefer to fill these T2G levels, and then we have to continue with the spin down electrons. Then when we finish with this manifold here, we can go to the higher level. In this way, if we do so, we can minimize locally the energy of the atom. But as I said, we have a high spin versus low spin. That means this crystal field splitting actually can be comparable, larger or smaller of the local exchange interaction. And then we have different possibility of the splitting depending of the local coordination. So we have tetrahedral coordination where the EG level are lower in energy with respect to T2 levels. So this can be justified in terms of geometrical arguments, but we are more interested in this cubic splitting where the T2G levels are lower in energy with respect to the EG level. And here I represent graphically these T2G levels and here the EG levels. So if we have this octahedral crystal field splitting, then, for instance, if we consider iron, we have the possibility that this exchange interaction is large with respect to the crystal field splitting. So we have this possibility. So suppose we have iron T+, so we have these oxidation states. In any case, locally we have D5 configuration. It means 5 electrons that we have to consider in these the orbitals. This means that we go on with 1, 2, 3, but then in this case we are the atom prefer to fill the EG level because we have this exchange interaction which is very large. So they want to maximize the spin and in order to satisfy the ANS rule. For the iron 2 plus, well, in this case we have D6 electron configuration, then we have 6 electrons to distribute in these D levels, and then we go as before. Of course, now we fill this reference energy level, but now we have to go again to the T2G in order to have this spin down electron. in the other case, small exchange interaction is small with respect to the crystal field splitting, then we have a different approach. And that means in the ion 3+, we have D5, again, 5 electrons. Okay, we go 1, 2, 3, but now it is more favorable for the atoms to continue to fill the T2G level, but here the only possibility is to consider a spin down electron in order to satisfy the Pauli exclusion principle. And then if you do so, the effective spin is actually, you have only one unpaired spin, so you have a kind of one magneton for this, Bohr magneton for this local atomic spin. Or in case D5, actually you are in this situation, then effectively you have almost zero effective spin for this ion. So you see that this interplay is very important when you study magnetism in crystals, because these local effects actually determine the local spin moment. Then of course, then you have to consider the possibility of this small spin moment to interact with other atomic moment. So the Siemens interaction, we have these energy terms. We have an interaction between the magnetic moment and a magnetic field. I just call magnetic field here. And in quantum mechanics, we know that this magnetic moment is actually given by the sum of two contributions. So we have the orbital part plus the spin part. Okay. But when we go to density functional theory, actually we speak about this Siemens interaction, but we introduce another kind of B field, which is called exchange field. And this exchange field in our density functional theory approach actually does not interact with the orbital moment, rather only with the spin moment. So we have this exchange interaction, which actually couples to only the spin moment. These are the basic implementation of density functional theory for the magnetic systems. So the key concept for understanding magnetism in solids are, of course, the electron spins. So we speak about these electron spins, but still we have to justify where it comes from. And here just start to put something more interesting, Lorentz transformations plus wave equation. So this is again a pictorial equation that we want to understand. Exchange interaction, we understood that Coulomb interaction plus permutation group plus symmetrization postulate, then we have this effective interaction between spins, among spins. Then spin-orbit interaction, we have already the feeling that this interaction comes from a relativity principle when applied to quantum mechanics. And then we just comment on Siemens interactions just to point out this effective exchange interaction in solids. And now there is another important concept that I want to recap here, and it's so-called charge localization. Of course, in the previous lecture, it was already introduced when introducing to the concept of pseudopotential. It was done beautifully by Ralph Gebauer in the first talk. So this charge localization usually is important to distinguish localized correlated electron with respect to the localized or band-like itinerant behavior. And this localization is related to the atomic valence electrons in a central atomic potential, which actually shows barrier effects which tend to localize these 3D and 4F valence electrons. So just in a qualitative approach, we want to highlight here the role of the so-called centrifugal potential here. So the inner atomic electrons determine the electronic potential in which the outer electrons move. And this potential actually can change depending on the quantum angular momentum channel, so can give rise to some localization property of these valence electrons. And then they are especially relevant for 3D electrons and even more for 4F electrons, for instance, in rare earths. So let me a little bit clarify what I'm saying here. So we started with this central field Hamiltonian in one particle approximation, independent particle approximation. Then we can use the radial the separation of variables, and in particular when we express this Laplacian in polar coordinates, we end up with this radial term of the electrostatic potential, then this angular momentum term, where you have this L dependence here. And it is called effective potential here. Then we can do our separation of variable here. And then one can parameterize following is later. This is just a qualitative approach by using some screening effect. So we have this centrifugal term, which can be recast in this effective potential. And then if we consider this effective potential for hydrogen-like atoms, then you see that it has a very different shapes, and in particular we have this strong dependence on L, Sp, and F. And then if we consider now for the 3D case, we have this 3D potential, but now there is this kind of well here, and then here we see that this atomic wave function is actually kind of localized in this same region. Actually, the effect becomes even more pronounced when we consider higher zeta. So we go towards rare earth. So here for ytterbium here, we see that there is a first well, then there is a pronounced barrier here, and then there is a very deep well. Actually, now the 4F will be trapped in this energy well here. And this is just the effect of the centrifugal potential. So, and this is a plot of the wave functions for this relevant case of gadolinium, and then you can see these 4F electrons which are very localized in space. So this poses some problem for the superpotential generation, but this was already discussed by Ralph the first day. Okay, so now we can go to some more realistic model in terms of band model of ferromagnetism. Still, we are on a qualitative approach. So essentially, we have the simplest band-like model for ferromagnetic metals is the so-called Stoner model of metallic ferromagnetism. I don't go into details into this Stoner model because, I mean, it requires some time. But for our qualitative approach here is we know that these 3D electrons actually in solids interact, giving rise to the so-called bands. And then we can describe these bands by using this density functional theory implemented in a periodic boundary condition, as you know, with the plane wave as basis set. At the end, we can focus on density of states, and we can represent it in a very simple way, like a semi-circle. So we can plot these those very schematic way, and this is just a question of nomenclature. So we think that there is an external magnetic field which fixes our quantization direction, okay, the zeta quantization axis. Then we know that the magnetic moment of this system would prefer to align along this direction due to the Siemens interaction. But now we know that the magnetic spin moment is related by this minus to the spin operator S, and then we can just put it Bohr magneton and sigma, and again minus. This means that this majority. We have a splitting of majority and minority electron spin. In particular, this is the Fermi level. We see that here the majority of the electron defined as majority bands or density of states, but they correspond to spin down electrons. And in this minority of the electron spin actually correspond to spin up electrons. So this is majority because the large part of the electron are considered in this band, in this occupy these energy levels, and this is a less fraction of the electron occupy these energy levels. In this case, you see that there is a splitting of the two bands, and this is called actually exchange splitting, which correspond to an energy separation for the two spin channel. Okay, so far so good, but now it's time to ask where does this spin comes from? So we are speaking about the spin since the beginning, but now maybe we want to have more insight. So I like to put this triangle here, because I think the vertices are very important to understand these variable here. I like to put here Hemi-neither and the keyword symmetry. I like to put here relativity, and here is Albert Einstein, and I like here to put quantum mechanics, Erwin Schrödinger. So formally, the spin arises by the combination of these three keywords. That means the contribution of these three are genius, I would say. And so why we stress our life with symmetry? Well, symmetry, Emmy wrote a very important theorem that is very important in particle physics. I know that there is someone from particle physics here in the audience, so maybe you would appreciate these comments here. So symmetry is important because it enables to generate families of solutions for a given one if some transformations leaves the dynamical equations invariant. Then, most important, this symmetry actually requires that there is a conservation of quantities, for instance, like charge, energy, or momentum, or angular momentum. And this conservation of quantities are connected to this Noether theorem. Basically, it states that if there is continuous systems of the Lagrangian, which describe our physical system, then there exists an associated quantity which is conserved by the system itself. So this is a very elegant way to show conserved quantity, or what is called constant of motion, sorry. And but in quantum mechanics, actually, we don't use this Lagrangian approach by using this Noether theorem, but we have a formulation thanks to Wigner that understood the crucial role of symmetry in quantum mechanics. Indeed, he received the Nobel Prize. And according to a theorem by Wigner, actually, symmetries can be represented by unitary operators. Sometimes they are anti-unitary, like time reversal. And essentially, conserved quantity are associated to these unitary operators, which commute with the Hamiltonian. So this is the projection of this theorem, so to say, into quantum mechanics without any quantum field formulations. So why relativity? Well, we know that this is a symmetry arguments, actually. According to Einstein, it's important that the physical theory must be coherent with the relativity principle, which states that there is the equivalence between the two inertial reference system. And then the only possible transformation which relate to these systems are so-called Lorentz transformations. Means that the physical laws must be relativistic covariant. So what is the problem with quantum mechanics? The problem is that if we consider the Schrodinger equation, it is not relativistic covariant. So in principle, it's not coherent with relativity, which is a basic symmetry arguments. Then Dirac found the new equation, which actually described the state of the electron, but it can be done in a relativistic covariant form. So he was able to derive an equation just by playing with mathematics, as we will see later, and constraining the equation itself to satisfy the relativity principle. And if we do so, then we have kind of a Lorentz symmetry, which implies that there exists a quantity that we call spin, such that, and it was stated by Dirac, L plus S is a new operator, J, which is actually a constant of motion. It means an operator which commutes with Hamiltonian by using the approach of Wigner. So it's already 1 hour that I'm speaking, so let me have a digression here. Let me relax a little bit. So beauty and symmetry. You know, symmetrical objects are very, very, very beautiful. If you have an object which is symmetric, well, it looks also beautiful. And indeed, someone was saying, well, a physical law must possess mathematical beauty. Or if one is working from the point of view of getting beauty into one's equation, one is on this sure line of progress. So you may start to think who is the scientist that was focusing this principle of mathematical beauty. Actually was Dirac. Indeed, he wrote this this equation, the Dirac equation, just playing around, as using his word, in search of pretty mathematics, looking for an equation which looks beautiful. Indeed, actually, if one recasts the Dirac equation in a covariant form, this is a high gamma nu, the nu, this is a like covariant formulation. These are matrices, but we don't care now. Well, this is considered among the most beautiful equations of mathematical physics. Okay, so let's now go in some details. We have this Schrodinger equation for the electron in an electromagnetic field. So we have to introduce the potential, and this is the electrostatic potential. Then we have the vector potential here. And then in quantum mechanics, we have this operator, which is in a real space representation given by this gradient and then this prefactor here. And now, what is the problem here? Well, the problem is that this differential operator in time actually comes linearly, but here the gradient comes with the power of 2. So they are not symmetric in this sense. But you know that in relativity, space and time, space and time variables are on the same level. So you have a quadri-formalism. And then Dirac was looking at kind of a linearization of this equation. That means let's consider an equation that can be expressed as a linear in time, but also linear in P, where P is the gradient here. So we have here the minimum coupling, which corresponds to the presence of the electromagnetic field. Well, the price to pay in this case that if you have 4 variables on the same level, then this psi becomes a 4-component object. And the equation was derived just requiring that the energy and a linear momentum actually satisfy the energy dispersion rule in Einstein relativity. And then this equation is a relativistic covariant. In this formulation, we don't see that, but we don't want into details here. We just use the three-dimensional approach, though we don't focus on covariant formalism. But what is important here, that this object here has 4 components, okay? It's called spinor. It's not a vector, it's a spinor, because it has a well-defined rules under transformation with this Lorentz group. Okay, but now we have to go in some details. So 4-component requires 4x4 matrices, and the standard representation presents these alpha and beta matrices in the following form, where sigma are the so-called Pauli matrices, which are very well known, and here a representation. Now, if one wants to look for solutions to this equation, since the field do not depend on time, then one can present the spinor in this with this time dependence. And if one do so, then one can consider the 4-component spinor as a 2-component bispinor. Okay, two component bispinor. So you can group a bispinor psi1, psi2, and the key spinor psi3, psi4. And then you can write this 4-component object by these two component spinors. This is a kind of form, but actually it will be useful later. And indeed, these 2 objects will have different transformation rule according to Lorentz, but we don't care about this now. But if we do this, then actually the Dirac equation becomes kind of a system of 2 equations written for the two-component spinor. So now this object here has 2 components. This object here has 2 components. And now here we have differential operators, sigma dot p, and then you can think like these apply to a 2-component object, like a matrix multiplication. And then one can express from this equation key as a function of phi, okay? Then one can rescale the energy. So we focus on this second equation, then we recast key as a function of phi. We can do that, and we have this expression here. And now what we do, we consider this key as a function of phi, and we put in the first equation. If we do so, then we end up with this following equation for the phi spinor. So we have here sigma dot P plus EA, and then here again this term here. We have to do some algebra, but we don't have time to do that here. But what we can note is that actually we could do a series expansion. So a series expansion means that we can focus on this term, then we can rewrite it here by exploiting this epsilon variable, which has this relevant expression here. Since this MC, well, MC square, this is the keyword in relativity, you know, m is the mass of the electron, c is the velocity of light, it is like 0.5 mega electron volt, so this effectively is quite small for valence electron, and we can do this power expansion. At 0 order, we can keep the following form, but then we realize that from this equation, where we express this component of the 4 component spinor in terms of the free spinor, which is a 2-component here, actually it looks quite small with respect to phi. And then it can be neglected. So we throw again away key, which appear small with respect to phi, and then it's called small component, and we throw it again. Actually, it is we are lucky that we can disregard it, because actually it is associated to the positive energy states and negative energy states, and then antiparticle states, but we don't care here. So we end up with a 2-component spinor formalism, and then by some algebra, by focusing on this equation, okay, by using some property of the sigma matrices, we can end up in this equation, which looks like a Schrodinger equation. So you remember this term here, and now we have this Zeeman interaction between an effective interaction between a moment which is entirely due to the spin of the electron, and then we can interpret this term actually arise from the intrinsic property of the electron, which is the spin, to which is associated this magnetic moment. And this is the interaction term, which is called as Zeeman term. And then we have this spin operator related to the sigma matrices. So this spin term is the interaction of the intrinsic magnetic moment of the electron with an external magnetic field. Remember that we are considering the electron in an electromagnetic field, and then this B field is interacting with this magnetic moment, which completely arises from Dirac equation. We start with Dirac equation, then we do some manipulation with these interaction terms in terms that we can interpret in terms of Zeeman, and then we are led to the conclusion that this is a magnetic moment associated to the spin of the electron. Then there are other formulation here. Okay, so this is a way to show the existence of the spin. There are other formal ways, either in a Lagrangian approach or some unitary transformation that we don't even consider the 4-component approach. So it's a very simple approach to show the existence of the spin. And then we can recast this equation, and then we have, if we consider also higher order in this expansion, then we arrive to a non-relativistic Hamiltonian. Looks like really a Schrodinger equation here. And now we have higher terms, which one is the higher order correction to the kinetic energy. Well, this is the Zeeman term, so we already mentioned it before, so we write it in a separate form. And look here, this is the spin-orbit interaction terms. So we started with the Dirac equation. We arrived now to the formal expression of the spin-orbit interaction term. For innermost electron of hydrogen-like electrons, it goes from as a zeta 4 variation. And then we had another term here, which is called Darwin term or contact term, which is effective only for s electrons. We can do the manipulation on the kinetic energy part, and then we end up with this expression for this total moment where we have an orbital part plus a spin part interacting with this B. Actually, this orbital part usually is disregarded in the following approach. And then if we have this mass velocity term, actually this term leads to the contraction and stabilization of sp electrons. And on the other hand, it leads to expansions and destabilization of the f electrons. Then we have these spin-orbit interaction terms, where it gives the energy splitting of the orbitals with the angular momentum, and then we have this Darwin term. So essentially, we in our computer simulation, we can we can switch on the spin orbit, we can switch off the spin orbit, and we can do what we call a computation experiment. So formally, if we don't have a spin orbit coupling, means that the Hamiltonian is actually, this L is a constant of motion, so it commutes with the Hamiltonian, S commutes with the Hamiltonian. Then we have these operators H, L square, L zeta, S square, S zeta, which form what is called a complete set of commuting observable. By specifying the eigenvalues of these operators, then we can specify in a unique way the state of the system. And then we have here the algebra of the angular momentum for the angular part, angular momentum here, and here for the spin angular momentum here. And then the basis set, actually one can build as a tensor product of these basis set here for the which are eigenstates of this angular momentum operators, and then the spin part here. And then in terms of symmetry, actually you are fine if you consider just the group of the crystal Hamiltonian. But when you explicitly consider the spin orbit term, it means that you are explicitly considering the presence of the spin, okay? And then it happens that this operator does not commute with the total Hamiltonian, neither does these S operators. Then you have to define this J, L plus M, and then you have found that this J operator actually commutes with the Hamiltonian. So it's a constant of the motion. Then its eigenvalues can be used to classify the quantum states of our system. So now we have another CSCO, L square, S square, L square, S square, J square, and J zeta, and then we have here the total Hamiltonian. This means that we have again the angular momentum, but now for J. Then we have this relation for the possible J values. And then we can easily compute this L dot S in this basis, and we can refer now to this expression in terms of this J, MJ basis. And we can go from this basis set into these bases which actually diagonalize this L dot S by using this so-called Clebsch-Gordon coefficient. Essentially, in a sense, from spherical harmonics, you define the so-called spin angle functions. And then, but here you have additional complication because you have double groups, which are required in order to deal with the symmetry properties of the electronic states. I think I can summarize this part for the time being, and now there is an important part that I have to discuss, so let me summarize. So we see that the spin actually derive from the Dirac equation, which is the equation which is coherent with the relativity principle. From a four-component formalism, we end up with some approximation in a two-spinor formalism, where these are spinors and not vectors, because they are well-defined rules, transformation rules, according to Lorentz transformation, and then can be connected to the so-called irreducible representation of the group SU2, that is especially unitary group 2 by 2. And then we have to use the double groups in order to exploit to describe the electronic the symmetry of the electronic states in the system. And we have seen that this spin orbit interaction has a true relativistic origin. And we have initially formulated some qualitative arguments, and also last week Professor Blugel mentioned this relativistic interaction of the electron, and which give rise to the so-called Rashba effect, by the way. And then we have other comment here, in particular magnetic system, the electronic states and their energy depend on the direction of magnetization with respect to ionic position. This is highlighted when you consider spin-orbit interactions, where there are different effects of the spin orbit on d s p states and also d and f orbitals. And spin is important even if the material is not magnetic. And now there is there are interesting topics in modern computational magnetism, like Rashba effect, which is relevant even if the system is not magnetic. But still, you have spin-related properties in this case called spin textures, which are important to describe also from a theoretical point of view. So now let's go towards the last part of the talk. Just a few words about density functional theory. Of course, we don't go into details because it was already discussed in the previous lectures. So essentially, we shift our attention from the full many-body wave function towards the charge density. It was stated by using the Heisenberg theorem, and then the Kohn-Sham approach, where essentially an interacting system is mapped into a non-interacting reference one. It's a completely first principle of ab initio. You just define the geometry, nothing else, and then you go on. Eventually, you introduce some approximations. Okay, so far so good, but let me go back to Dirac again, because it was really a genius, and he had some great intuitions. Well, he defined the fundamental equations, and then everything is known in order to study materials properties. But actually, the equations look quite complicated. Then you have to resort to approximation, and actually, all modern computational method relies on approximations. But still, you don't have to focus your attention on a complex wave function. Rather, you should shift your attention on the density. And it was stated by Dirac in 1930, and you can have nice comments about this quotation here if you read this Review Modern Physics by Jones of 2015. So actually, the intuition was shift the attention towards the density, and it was done perfect. And Heisenberg theorem did a very nice job here, because build a completely a theory which is equivalent to the Schrodinger formulation. Essentially, you shift your attention from this system, pictorially represents this interacting system, then you go towards, you map it in a non-interactive reference system. You keep the same number of electrons, you keep the same ground state energy, and then the external potential actually becomes kind of a Kohn-Sham potential. And density functional theory is very well used nowadays, and you see that how the publication rate increases about this application using DFT. And now, after the talk by Yuri yesterday, you know that a large fraction of these publications are done actually by ESPRESSO implementation of DFT in plane wave basis set. Okay, but let's review basically density functional theory now. So we have an electron system in an external potential, a nuclei, or a pseudo potential representing the nuclei for a non-degenerate ground states. Now the many-body wave function psi and the external potential are uniquely determined by this, and so there is a one-to-one correspondence. And then you can define an energy function which is stationary with respect to the variation of the density. And you end up with this kind of analytical expression, but it's not so analytical because we don't know in principle this analytical form from G, which is actually a uniform term, a universal functional here. So one has to approximate this G. Then in the Kohn-Sham approach, thanks God there is this independent system, because now we can express the kinetic energy of this system, and then essentially we can exploit this kinetic energy, we can subtract from this universal functional, and then we end up by another functional which is unknown, but it is called now exchange correlation functional. We have to keep in mind the conservation of the particle, so n is the number of electrons, and then we can implement this in a Lagrange parameter lambda. Then we can do our variational principle here, and we end up with this so-called Kohn-Sham equation. So we have kinetic part, the external potential, the alternating potential, so to say, and then something which is related to the functional derivatives of n, well, the exchange correlation function with respect to n. Of course, in order to evaluate this functional derivative, one has to know at least an approximation for this exchange correlation functional. And so you know several approximations as discussed by Professor De Gironcoli last week. But now we want to generalize this formalism by including the spin, and then we have spin density functional theory. So there are several approaches. I think the first approach was using the covariant formalism by using the J-nu four-dimensional vector current. This is rather complicated, but we don't state it here. Rather, we use the approach by Bart and Herid, and essentially, we suppose already that there exists this Kohn-Sham system, and then for it, since we are dealing with spin, since we know that we have to do with the two by two formalism. It means we have a spinor, which is a two-component object. So we don't have a scalar density of the system. Rather, we have to play with a density matrix here. So then you define this density matrix. I don't go into details. You can define it from the full many-body wave function by appropriate contraction terms and so on. But at the end, you have this density matrix, which is now the relevant variable that in terms of which you want to establish the spin density functional theory. And you have this spinor here, where two different functions. There are two different functions of the same spinor. Then you can have plus minus for alpha beta or spin up and spin down. Then you can write this formally this density matrix by using this projector here, and then you can highlight the matrix element, keeping diagonal in a real space representation. Then you have alpha and beta, which are the spin indices. You can have this representation in terms of the spin, the spinor component here, and then you have this representation in terms of elements of this density matrix. Usually they are called coherences, and these are these are populations. These are the off-diagonal terms are called coherences. Well, this matrix is actually Hermitian and depends in each point of the space. But the electron density can be now evaluated as a trace of this density matrix. Actually, this is this is a standard quantum mechanics. Also in standard quantum mechanics, you can introduce an equivalent formulation in terms of wave function by using this density matrix. And then let me have some digression here. So a little bit of algebra here. So you go to your standard quantum mechanical textbook. You know that every M matrices, which is a 2 by 2 Hermitian matrices, actually can be expressed as a linear combination of these four relevant matrices. So these are a basis matrices in this matrix space, and then you can express these coefficients A and B, actually B as three component and looks like a vector, and you can calculate this coefficient by using these M matrices, M matrix like a trace for A, and B for, you can calculate like trace of M times sigma. Remember that M is 2 by 2 sigma, 2 by 2 matrix, and sigma are 2 by 2 Pauli matrices. So you can take the X component, and then you end up here with the X component of this B vector. Okay, so far so good. Hermitian can be diagonalized. You can evaluate the eigenvalues. You can express in a rather complicated way by introducing these theta and phi angles, which are actually connected to the matrix element of these M matrices. I don't go into details here. There are just standard use, but look at these matrices. It's quite interesting in its form. It is actually, it is called spin 1 rotation matrix, and is a rotational matrix actually, which actually acts on the spin space. And then in terms of this matrix, you can diagonalize the M matrices by this unitary rotation. Okay, so far so good. Helpful rotations. Why helpful? Well, you have a global reference axis here for instance, a crystal axis, and then you have a local reference frame, atom-centered, for instance. And then you have a kind of vector here, which is referred to this local reference axis. Well, in this reference axis, this vector actually has a very useful representation. It's just a norm times 001, where 001 is referred to this component in this local reference basis. Then, of course, you can go back to this reference system, laboratory system, or global reference system, and then you can express this as like this Cartesian component in this old global reference system. Well, so rotation in real space actually induce some unitary rotations in spin space, which are represented by this spin 1 unitary matrix. Well, what is important that this mean value of the spin, actually it's S, behaves like a vector. So it transforms like a vector when you have a rotation in real space. But this rotation in real space can be mapped in this rotation in spin space. But now you have actually to one U matrix, you have another matrix. I mean, if you perform a 2-pi rotation in real space, you end up with the same system. You go to the identity, so to say. But if you do a 2-pi rotation in spin space, you end up with minus U. So in order to recover the identity, you have to perform a rotation of 4-pi. Then you have essentially two matrices associated to one rotation in real space. This is called two-fold homomorphism. It is the origin of what is called double groups. Then changing variables. Okay, now we can express the density either like a trace as we've done before, or we can exploit this spinor here. So this is a two-component object, which is a column vector, a column format, and then this is a row format. So a row two-component object, spinor, times a column two-component object, then you have a density, charge density here, and then you can evaluate the magnetization density by this expression here, where you have the spin operators. Then again, this representation in terms of density matrix, but now if you have the density matrix, you know by previous decomposition, okay, now we forgot about the units here, I will just keep the discussion very simple. We can calculate the density matrix as a trace of the matrix, and then we can evaluate the magnetization and density by using this trace of n matrix density matrix times sigma. And then we end up with n and m. Okay, so starting from n, we can always define these two variables. So this is scalar density, and this is a three-dimensional vector density. But now, suppose we know these two objects here, we can build our density matrix by the previous decomposition. As I said, forget about the units here. There should be some ball magnet somewhere here. And then we end up with the density matrix. So we can exploit either to the formulations. So we go back to the variational principle, and then we can explore this variational derivative here. And of course, we have to consider this in terms of the density matrix. Then, if we do so, essentially we end up with the matrix equation here, where this psi is actually a two-component spinor. I just write generally as a psi, and we have this object here, which is again a 2x2 matrix. Well, this is diagonal, and here we have the identity. Then we can express the component of this spinor here with the first component and second component here. So this is a complex component here, a second component, and here we have the eigenvalues up and down referred to spin up or spin down. Of course, when we have to evaluate this object, we end up again with 2x2 matrix, which we can express in the following form. We can express also the matrix indexes, so this identity becomes this Kronecker delta alpha and beta in the spin indices. So here it is still diagonal, but here we have these terms, which is in general not in the diagonal form. Here we highlight the index of the component of the spinor, and here we have epsilon high, so here there should be I in the spinor component. So how we can evaluate these terms? Actually, remember the previous decomposition. So we can represent this 2x2 density matrix by using the Pauli matrices. So these four matrices, and then we have this decomposition. Okay, again, don't focus now on the units. We can always express this density matrix as a combination of a scalar term time identity plus a linear combination of the Pauli matrices and a coefficient here, which actually is recast in the form of a vector. Then we can express all these components in terms of n and mi component. Okay, so far so good. So the idea is do the same for this complex object. Indeed, we can do. So you see here it looks like a trace, and this is actually the diagonal component. Then we have off-diagonal terms, which can be recast in the form of a magnetic field. Actually, it's called exchange correlation B field. Then we can introduce these new variables, N, M, and then we have this expression for exchange correlation potential in terms of alpha and beta indices. So here we have diagonal part, the exchange correlation potential, the scalar potential. Then we have in general a B field, an exchange correlation B field, which is coupled to a term which looks like a magnetic moment. We know that now this term is like a magnetic moment. And then this is the standard equation that we should solve when we are dealing with a spinor approach to density functional theory. And then it looks quite complicated. And we have this B field, which looks like an effective magnetic field, as I said, is called exchange correlation magnetic field, which is responsible for the onset of the magnetic order at low temperature, ideally at 0 temperature. And essentially, it recasts the anti-symmetrization postulate and spin in density functional theory. Okay, so it's not a trifork approach here, it's just DFT, but now there is the emergence of this exchange correlation B field, which comes from the exchange correlation functional. Now, what is important here, this guy, this is a median, is a density matrix, but locally can be diagonalized for each R. Okay, I think I have to go a little bit faster because my time is over. So let me summarize. Non-magnetic, non-spin polarized system. It was done previously. Non-interactive system, reference system, there is no spin variable here, there is no magnetic field, forget about this. But you keep your energy function as a function of the ground state density charge, scalar function. Magnetic spin polarized, in the most general term, you have this interacting system, and now you explicitly put for each electron a spin variable, okay? Then you map to the Kohn-Sham reference system, and each Kohn-Sham electron now has a spin associated with it. Okay, so it's just pictorially speaking. And now your energy function can be expressed either in terms of density matrix, or you can use these more intuitive variables N and MR, which are the magnetization density. Okay, so far so good, but now we have to understand a little bit these equations, otherwise we are a little bit confusing. So fictitious non-interacting electron system, a general case, non-collinear. Well, there is no reason why this vector should be along the same axis, okay? What does it mean this in terms of spinor? It means that there exists in non-collinear magnetism, there is no any unique quantization axis. So exists a versor which depends on how high the electron that you are considering, such that the spinor of this electron is actually an eigenstate, for reference here with eigenvalue plus h bar divided by 2 times psi. And then this spinor actually has two components which are in general different, but are the components of the same object, okay, the same spinor. And then you can express here by explicitly put forward the spin basis, 1, 0, and 0, 1, spin up, spin down. And these coefficients, you just refer with an index up and down. Collinear magnetism, there exists a unique U axis and since it is unique, we call it zeta, such that the psi can be either eigenstate with the eigenvalue plus 1/2, so to say, and now the psi spinor has only one component different from 0, for instance, the upper one, okay, and this must be 0, okay, or you may have that the electron has a spinor, which is eigenstate of this spin spin operator, which eigenvalue minus 1/2, but now this spinor looks like 0 and a component, lower component, which is different from 0. So actually now these phi up and phi down are different components of different spinors. Okay, so the electrons in this collinear case have all either a spinor of this form or the other form, and then means that essentially the Kohn-Sham electrons, pictorially speaking, will have the same spin along the same reference axis. Some can be up and some can be down, never mind. So non-collinear magnetism, there is no unique quantization axis. This Hermitian, I stress it's Hermitian because you can always diagonalize in each point in space, and actually this is explored in the implementation, because the problem is that the exchange correlation function has a form, for instance, in local spin density approximation are diagonal in the spin density matrix in every point, and then it poses some problem when you have to compute this exchange correlation function in complicated cases. Anyway, we have equivalent formulation in terms of different variable. For collinear magnetism, there exists a unique quantization axis. This matrix is always diagonal for each air in space. So we have this the spin up charge density and spin down charge density, and then you can evaluate the magnetization density along zeta by using this this definition. Okay, give me some more time. Let me comment on this. So as I said, equivalent formulation of the density matrix, you can explicitly put the charge density and the magnetization density in the matrix elements, and then you can evaluate the charge density by using the trace, and then if you do that in the collinear case, you just end up with this and blah blah, and the sum of the spin up density and spin down density. Then you can evaluate yet another equivalent form to evaluate the magnetization density. Charge density you can now express even by explicitly writing the component of the spinors. So here for the charge density and for the spin density, you see that it looks rather complicated in terms of the component of the spinor. Then you can recast in much more simple form. You see that in this case, S zeta is just the difference of the population for spin up and spin down times some constant. Okay, so I think we have a kind of stop slash summary. Let me recast the questions here. So non-spin polarized system. Well, okay, we have a exchange correlation function, but it is the same for either spin up or spin down. Then you have a spinor up or component up and down. Then this eigenvalue. This eigenvalue is the same for spin up and spin down. What does it mean here? This means that, well, you have an electron, you solve your Kohn-Sham equation at each k point, then you have to fill these energy eigenvalues by this electron. Now you know that each eigenvalues is the same for spin up and spin down. So it looks like that you have to solve the equation for spin up once time. Then you have the same result for spin down. In this sense, the equations are rather simple. Okay, now spin polarized system, collinear case. What does it mean collinear? Well, we know that the two spinors have either one component up different from 0 and the other 0, or in the other case, one component up 0, the other, the lower one different from 0. This means that when you write in this equation, you have kind of a system of two equations, which looks independent. You have epsilon I, which depends on the spin, which is in general different from epsilon I, which differ depending on the other spin down electron. And they are not truly independent because this Hartree potential actually depends of both spin up and spin down density. Okay, so in a sense there are some hiding constraint in this equation, but still you have these two series of eigenvalues are in general different. So this means that for each k point you have to solve the first equation, then you have epsilon I up, and then you have to solve another time for the same k point the down equation. That means that you have kind of solved twice the same reference system. And now for the non-collinear equation here, you have a much more complex case where now you have the eigenvalues which are associated with these two-component spiral. So this means that now if you have an electron to define your ground state system, then you have to consider at least n eigenvalues, because each eigenvalue will be referred to one electron. Okay, here each eigenvalue was referring to 2 electrons. Here we have, for each k point, 2 eigenvalues, which are referring to 2 different spin states. So from top to bottom, you increase complexity, and this means computational cost and also other technical details. So I can quickly summarize things here. Non-collinear magnetism usually reduces symmetry. The magnetic unit cell can be larger than the chemical unit cell. For instance, if you want to simulate entire ferromagnetic configuration, you have to build a supercell, and then you have to define spin up and spin down according to your system. And usually you have to be careful with the k-point mesh sampling in order to compute accurate values of your relevant variables. Okay, so now computational magnetism, we can evaluate the ground state total energy in terms of density charge and then magnetization density. Then we can evaluate this total and absolute spin magnetic moment. Probably Pietro will comment on this on the exercise. You can look at these values in the output file. Then you can do the band structure calculation. You can do for non-spin polarized, for spin polarized. You can split collinear or non-collinear, and then here the bands refer to the spinal bands. Then you can compute the density of states. It is non-self-consistent run. You can resolve the total density spin up and spin down. You can even resolve the density of states locally for each atom, referring to spin up and spin down. Local moment, you can evaluate the local moment, magnetic moment, or you can even evaluate this magnetization density in the real space. You can even plot the so-called spin density. So a qualitative example here, and we are going towards the ons and so on. So iron BCC, actually this will be an example of, later in the tutorial. Non-magnetic, we can force the sim to be non-magnetic. Okay, so the energy actually is higher with respect to the magnetic case, but the dose density of states looks the same for spin up and spin down. We didn't break the spin degeneracy. Okay, so they are just the same. Good, but now we force. We break the symmetry, and the system evolves towards a low energy state, which is now magnetic. So it's kind of a symmetry breaking here. And now the density of states looks different. They are spin up and spin down. You see here majority spin electrons. The majority electrons are occupied here. These are minority spin, where actually you have a large fraction of unoccupied states. Then you can, this is the total dose for the iron when it is magnetic, but then you can project on these states, and then you see that actually this splitting between the relevant peaks here actually is called exchange splitting, and is mainly related to the exchange field acting on these states, which split them. Okay, this was the exchange splitting that derives from the exchange correlation function, due to this fictitious magnetic field. Okay, I think now I can go back to the previous slides. So now probably we have some way to understand what are these errors here. So we have a collinear case, we have a ferromagnet. So it means that we have the lattice sides, then we can integrate the spin moment in a sphere around the atom, and then we can define a spin moment for each sphere. Sorry, I had the voice in background, so you can keep the microphone off. Then for the entire ferromagnetic case, actually we have a standard arrangement of the magnetic moment. So you have up and down. So you can integrate your spin density or magnetization density around one sphere. And then you have spin moment in one direction, spin moment in the opposite direction in the neighboring atoms. They are collinear, okay? Then in transition metaxide, you have plenty of anti-ferromagnetic spin configurations. You have ferromagnets. The spins do not compensate. You have still a residual magnetization in the unit cell. Then we have a much complicated non-collinear structure. Weak ferromagnets, it's non-collinear. It looks like anti-ferromagnet, but the spins are tilted. So there is an uncompensated magnetic moment. Can be strong tilted, can be even stronger. And for instance, manganese delta, the phase of manganese delta is a very complex non-collinear structure with, if I remember correctly, 52 atoms in the unit cell. And it was an example of non-collinear magnetism, which was calculated using density functional theory. Then, of course, you have plenty of much more complicated structures, spin spiral, incommensurate structure, and skirmions, for instance, that Professor Blugel was mentioning. So before closing this lecture, let me acknowledge some people here. So in particular, Yutin Hu, she was so kind to help me in some graphical rendering of this talk. Then Kuniko Yalanoses is my present collaborator, and is also was helping me for doing some exercise for this tutorial. And Joao Gonçalves is currently my collaborator. I have to thank Professor Joachim Storr because he kindly allowed me to consider his book to prepare, in order to prepare this lecture. I will mention later in the reference list. Of course, Pietro De Lugas for useful feedback on this lecture presentation. I want to thank all the tutors of Day 7 Magnetism because I'm sure they will do a great job today. There are many people that I should thank because all this expertise in magnetism, I mean, the small expertise I have was due to the many people that I have discussed during the years, in particular to my collaborators in CNR, Picozzi, Barone, and Disante, and these people from Bilbao Crystallographic Server. You know that this is very useful for computational magnetism. Radaelli and Branton, which are very expert in computational magnetism and also magnetic symmetry, and many people from China University, and in particular Shanghai University. And sorry, 1 minute just to comment the bibliography. I put a lot of effort to select the relevant books that I find it useful for beginners, but also for advanced users. In particular, this book is very nice because it's very complete. It's an experimental book, and but it has also a lot of theory. Not very deep in details, but it's very good for beginners. This book from Giustino is a useful book for practical application of density functional theory. And the one from Kluber is very good for itinerant electromagnetism. Then other books that I mentioned here, of course, the Martin book, the Biblia of the density functional users. Advanced book in quantum chemistry, I mean, the solving of Dirac equation in 4-component formalism as another field in quantum chemistry, and this is a very good book for these applications. This is atomic book, of course, the quantum mechanics from Tanudi, and then this one which is a general approach for magnetism and magnetic materials. It is a very new one, very recent. References, Michelane, many people has worked in ESPRESSO community and also implementing many things, so it's important to mention the relevant papers. So actually this is a general paper. It's about spin orbit from a chemistry point of view. I think it's very useful because it highlights many interesting things. This is a review paper, very cited. It's very good for quantum chemistry. And then, of course, this paper by, I think, Ralph Gebauer, Implementation of Non-Collinear Magnetism, this paper by Dal Corso, the same here with Dal Corso, and this spin orbit coupling in ultrasoft potential, papers by Dal Corso, that actually is the expert on the potential generation by using spin orbit coupling. And then also this paper by Ralph Gebauer and Stefano Baroni. And actually this paper, it comes from the VASP community. It was the non-collinear magnetism, and it was the application of the magnetism in manganese, which is very complex. And then this is one recent paper that I just found these days, and it's actually density functional perturbation theory within non-collinear magnetism. It's very instructive because it recaps the formalism, and then it discusses the so-called local spin collinearity and so on and so forth, and then the problem that we have to deal with when we compare the exchange correlation functional and we want to compute for the magnetic systems. And then here, just a miscellanea. Sorry, I just put some reference paper that comes from my expertise. So these are advanced application of magnetism with the multiferroic system in complex material, which are hybrid compound. This is a Rashba effect. That means advanced application of spin orbital reference properties, which is very hot topic now in physics. Some reference from my colleague, in particular spontaneous skyrmionic lattice, which is a very nice application about non-collinear magnetism by DFT. And then I like to mention this paper, which is actually by, I think, Pietro De Lugas. It is spin vortices and donouts. So it's a very, very fancy paper about the spin textures applied in non-magnetic system. So you see that the spin is a hiding variable. Sometimes it shows up with some spin vortices, and I suggest you to consider this paper. I think my time is over, so I really thank you for your attention, and I hope you got the main important message from this talk. Thank you very much.
Thank you, Alessandro, for the very thorough overview of the topic. Very interesting and entertaining. Maybe it's too late for questions. There is just one from Amal Aldarresh that asks if it's possible to compute exchange interactions using quantum espresso or any other DFT code.
Well, of course, this exchange interaction means that in principle you have two kind of comments. One is using the Heisenberg Hamiltonian in terms of these JIJ constants. Sorry, Pietro, can you switch off the microphone?
Sorry, yes. Sorry.
And this means that you have this isotropic exchange matrix, and you can map this matrix in DFT simulations. Means that you are mapping the Hamiltonian in different spin configuration, and that basically you refer to the energy differences in total energy with respect to the spin configuration. It can be mapped, these differences can be mapped in this linear system using this Heisenberg Hamiltonian, okay? In this way, you have an estimate of your J's, and then by using this mapping, you can even extend to use some other approach like statistical approach using Monte Carlo, and then including temperature and so on and so forth. Then there is another issues that you have to consider, like the model Hamiltonian approach and correction for these states, which are DFT plus U, DFT plus U plus V, and actually recently DFT plus U plus J, where J actually is a kind of a local exchange interaction, where I don't go into details here, I'm not really an expert, but I really suggest you to have a look to the papers by Matteo Cococcioni, who did a lot of work along this implementation. There was these recent developments by using this J implemented in some Hubbard Hamiltonian in order to stabilize actually your high spin states in case you need to stabilize that. So there are some critical cases like Kuplik size, but that by symmetry, you cannot stabilize an insulating gap. Rather, you have to either to include some distortion, or you have to use this J approximation, your Hubbard Hamiltonian, in order to to stabilize the high spin states. I hope I answered your questions.
Okay, thanks very much. And let's thank Alessandro again for this.
So, okay, I will be answering during the slides.
And yes, for the questions, for further questions, please use Slack or also the chat on YouTube, and Alessandro will be able to answer you there, and also on Slack. Also, the tutors will help with easier questions. I think that we ran really late. We are at 10:30, so we should actually start now the tutorial.
That's 5 minutes
to have 15 minutes of break, and then start here. Come back here at 15 to 11 and start the tutorial then. Is it?
Okay, thank you very much. Thank you.
Thank you, Alessandro. It was really a great talk and thorough, with really a great lecture. Thank you very much.